This is a LiDAR360 version 5.0 terrain module tutorial. Let's start with the remove outliers, smooth points, and subsampling section. Subsampling point clouds, namely reducing the number of point clouds. LiDAR360 offers three methods for resampling: minimum point spacing, sampling rate, and octree. The default sampling type is minimum point spacing. Users need to set a minimum point spacing between 2 points so that the minimum three-dimensional distance between any 2 points in the sampled point cloud will not be less than this value. The larger the value is set, the fewer points will be kept. Common noises include high-level gross errors and low-level gross errors. The Remove Outliers tool aims to remove these errors as much as possible and therefore improve the data quality. If there are not enough points found, the algorithm will not be executed. The algorithm of this function can be performed repeatedly to improve the denoising results. The outlier removal results is limited if the noises are too dense. Section editing function allows the user to display the point cloud data of any rectangular area in the main window and the section window, which is convenient for the user to view, measure, and modify the class. In this case, the profile view tool can be used to measure the thickness of the point cloud in order to determine whether smooth points processing is necessary. Also, record the thickness before smoothing for later comparison. The Smooth Points tool smooths the LiDAR point cloud based on the neighboring points, making the point cloud look more consistent. The default smoothing type is XYZ, meaning that in the 3D smoothing process, the points on the vertical plane are smoothed in the XY direction, and the points on the horizontal plane are smoothed in the Z direction. Please refer to the user manual for the descriptions on other parameters. Use the Display by File visualization option to render the point clouds from different files to different color values and intuitively distinguish point cloud data, which are from different point cloud files. Then use the measurement tool within the Profile View tool to check the point cloud thickness. Again, compare the recorded thickness values to tell the difference between before and after smoothing. After the smoothing, the point clouds are thinner than before. The second section includes tutorials on DEM, DSM, and contour line generation. Before one of these models can be generated, the ground points of the point clouds need to be classified first. Please refer to the Classify Ground Points tool for more information. A digital elevation model is the digitized simulation of terrain through limited topographic elevation data, such as the digitized representations of terrain surface. It represents the ground elevation with a set of ordered numerical array. LiDAR360 provides three kinds of raster cell interpolation methods: inverse distance weight interpolation, Kriging interpolation, and triangular irregular network interpolation. For more information on the interpolation methods settings, please refer to the grid parameters section in the user manual. A digital surface model refers to the digital representation of the height of the surface, including the buildings, bridges, trees, etc. Compared to a DEM, a DSM contains more elevation information for buildings, bridges, forests, and other surface objects that don't exist in the DEM. DSM is based on the DEM and further covers the elevation of surface information, other than the ground, same as the DEM. Please refer to the grid parameters section in the user manual for interpolation settings instructions. The Point Cloud to Contour tool extracts elevation contours from input point cloud data by developing a triangular irregular network from ground class points. This is then used to construct lines of equal elevation that are output as a polyline through tin to contour. For more instructions on parameter settings, please refer to the Point Cloud to Contour section in the user manual. The Generate Tin tool generates a regular triangulation model based on the point cloud. The software adopts custom triangulation model file format LiTin. There are two methods to generate tin: Delaunay and spike-free tin. The results consist of three types of tiles: tile by scale, tile by width and height, and no tile. The optional flatten tool is used to flatten the specified range based on the user input files. For more information on each of these parameters, please refer to the Generate TIN section in the user manual. The model file stores triangular irregular network models generated by DEM or DSM. The model files can be edited by various operations, such as flatten height, smooth height, repair no data, repair height by variance, repair height and delete height by using the model editor. For polygon selection, left-click to add the polygon vertex, double-click to finish the selection, right-click to back one point or clear selection. Before finish, unlike screen selection tool, you cannot select an area that exceeds the data range. Left-click to start the lasso selection, move to add one point and double-click to finish the selection, right-click to back one point or clear selection. Before finish, unlike screen selection tool, you cannot select an area that exceeds the data range. Screen selection is similar to polygon selection, but for screen selection you can select the area that exceeds the data range. For a specific range, the existing 2D shapefile can be imported and the polygon is identified by the software as the editing area. In the Flatten Height tool, you can set elevations for selected area range models to specified elevation values for rivers or waters that have the same altitude. The Smooth Height tool can smooth the selected area range model, using image mean smoothing to process the model in the selected region point by point. It is suitable for smoothing DEMs to generate smooth contour lines. The kernel size can only be odd numbers. The Repair No Data tool used by linear interpolation to calculate the elevation value of no data values in the area. The Repair Height by Variance tool is used to repair the noise caused by noise, according to the variance of its elevation value with the neighbor point to determine whether it is a noise. Bilinear interpolation is used to calculate the elevation of the noise point. The Repair Height tool is used to repair the elevation in the specified range. The bilinear interpolation method is used to calculate the elevation of the perimeter conditions. The different types determine the areas to be repaired. There are 3 different types: all selected as a region of no data, value elevation range, and internal no data value. Use the Delete Height tool to delete the selected point elevation point. The LiDAR file is generated by the irregular 2.5D triangulation model based on the point cloud. It can improve quality of contour lines by editing operations, including flatten height, smooth height, vertex, addition and removal, etc. LiDAR files can be edited by using the LiDAR editor. Use the Add Single Point to add a vertex in the triangulation model. Users can select the source of the elevation value. This function is suitable for local editing. The following 4 options are provided to define the height source. The default is from the surface. The elevation is determined by triangular interpolation, max z from the surface, the maximum elevation of the model, min z from the surface, the minimum elevation of the model as specified user input, a customized elevation. Use the Delete Single Point to delete a vertex from the triangulation model and reconstruct the triangulation with its neighboring points. This function is suitable for local editing, removing noise point, or misclassified points intervening the generated terrain trend. Use the Tin Flatten tool to flatten the elevation of certain areas by either using the mouse for area selection or by importing file with polygons. The default flatten mode is called Same Height, which means the flattening elevation will be the average elevation of the triangular irregular network in the selected area, while the adaptive height model is based on a fitting plane created by 3 selected points, as marked in the table. Add brake line by mouse interaction. You can select the brake line type, elevation value, and whether it is closed. This function is applicable to water bodies, highways, and other situations where the terrain changes violently. It is used to distinguish the trend of the terrain around the fault line. Use the Delete Brake Line tool to delete the selected brake line. The Query Dip and Strike tool is used to calculate dip and strike automatically, or based on the point clouds selected manually. Related Analysis tool and Result Report are also available. Load the point cloud in the viewer. Click Geological Analysis Query Dip and Strike, and the toolbar will show in the viewer. In the Query Dip and Strike window, there are several buttons: Export Data Query, Dip and Strike automatically, Query Dip and Strike, Clear Data, Statistic Report. Adjust radius and settings by clicking the Query Dip and Strike button. A round selection box will show in the point cloud viewer. You can also adjust the radius of the circle after selecting the point cloud by the round box. The dip and strike info will show as a 3D model in the viewer. Meanwhile, a query record will add in the table below. The Auto Query Dip and Strike tool can automatically calculate dip and strike and add the record in the table below. Import the point cloud and select the class of point cloud to be calculated. Default setting is ground point for octree level. The higher the level, the fewer the number of point clouds contained in each octree node. The larger the value is set, the finer the queried facet. Otherwise, the larger the facet. For more information on facet types, please refer to the Query Dip and Strike section in the user manual. The larger the distance threshold, the more points will be segmented into a facet, which means there will be more large facets. Minimum points per facet defines the minimum points of a facet. The larger the value, the more the points of a facet. Click the Merge button, select a polygon in the window as the target polygon. Pick other polygon in the window, and other polygons will be merged into the target polygon at the same time. The corresponding data in the table below will be deleted. Right-click to end the process. Click the Statistics Report button to do statistics and filter on the dip and strike. Set the interval for dip and strike statistics. The rows diagram and corresponding statistical reports can also be generated. When filtering, you can choose different filtering types and rendering types, and filter by setting. The minimum and maximum angle threshold, checking or unchecking the box to decide whether to show label axis and horizontal plane. The change detection tool can be used to calculate the relative height change of the two periods of point cloud and output it as a TIFF format image and an HTML report. In the image, red represents increase, green represents decrease, and other parts are displayed in grayscale on elevation values. The reference point cloud is the benchmark of the point cloud to be compared, which will be displayed in green in the image. The compared cloud is the point cloud to be compared, which will be displayed in red in the image. Each class in the 2 point clouds will be compared separately. Cell size refers to the side length of the grid that grids the point cloud. The smaller the value is set, the more detailed the change detection between the point clouds, and vice versa. The point cloud assigns a corresponding distance value only when the elevation value change is greater than the DZ tolerance value, and the point cloud is considered as no change if it is less than this threshold value, and the change distance is 0. Once the process is complete, detailed changes between reference and comparison point clouds can be further inspected by viewing the report in the defined output directory. This section analysis module is aimed at road cross-sections and tunnel cross-sections and mainly solves problems such as the design of reference cross-section lines based on point cloud and model data. This function is based on the actual measurement data to obtain the measurement section of each location or the real topographic undulation. It can edit and manage the measurement section. Finally, output the information of each section and generate the over-under excavation report. Activate the Section Analysis module under the Terrain tab. A Section Analysis toolbar will appear at the top of the data display window. Use the Create Polyline tool to create a reference section line by drawing a series of points with the mouse. This tool supports drawing multiple reference section lines. Click the Import Polyline button to open the Import Reference Line interface, which supports text files, graphic files, and vector files. Click the Extract Points Along Section Line button to extract the point cloud data around the reference section line. If a model file is loaded, all the vertices of the triangulation network within the model range will be extracted. Click the Add Polyline button to generate and add cross-section polyline. Either automatically or manually set the width and step length parameters for the reference cross-section. For more information on each of these parameters, please refer to the user manual. Clear all or some of the section polylines by using the Clear Section Polylines tool. Use the Save Section Polyline tool to save the created section polylines to text or shapefiles. Click the Import Design Cross-Section button to import the design section into the software. Support text files. The read section lines will all be displayed as design section lines. Click the Generate Road Section Chart button to generate the section chart of a given road set. Set the section thickness for the width of the section line. To generate a section view by using the point cloud data, choose the classes to be involved in generating the section set. The section step according to the distance threshold. Set the maximum length of the segment lines. Choose a type to decide whether to view from the top or bottom. For more information on these parameters, please refer to the user manual. Click and hold the left button on the mouse and move on the section chart. Users can view the section information at the position of the mouse in real time. Click the Generate Tunnel Section Chart button to generate a tunnel section chart based on the cross-section line. Click the Calculate button to bring up the Parameter Settings dialog. Click OK to generate the tunnel cross-section. Canvas can be panned and zoomed with the mouse. The Export section allows you to export the currently created tunnel section line, which can be saved as a 2D or 3D file. Image Export allows you to save a section of the current dialog box as a picture, and the save format is PDF. The user can set the resolution and size of the exported cross-section in the export interface. Use the Edit Section Line Nodes tool to edit the nodes of the tunnel section line. After editing is turned on, you can drag and drop the nodes. It is used to edit the wrong or noisy tunnel boundary. The tool will also allow you to export comparison report and take distance measurement. Use the Editor tool to either show or hide section polylines as needed, including draw line, orthogonal line, section line, and all. Other than the generation of the DEM and DSM, there are many other related topographic products, such as Hilshade, Slope, Aspect, and Roughness, which are all also supported by LiDAR360. The Hilshade tool obtains the assumed illumination of the surface by determining the illumination for each image element in the grid. The assumed illumination can be attained by setting the position of the light source and calculating the illumination value of each image element related to the adjacent pixels in the analysis or graphic display. The Hilshade tool can greatly enhance the surface visualization, especially when using transparency. Slope shows the depth of the terrain surface. This function analyzes terrain slope based on the DEM and generates slope images. Aspect refers to the orientation of the terrain slope, defined as the direction of the projection of the slope, normal on the horizontal plane. Slope direction is of great importance for mountain ecology. Roughness is an indicator that reflects surface fluctuations and changes in the degree of erosion. It is generally defined as the ratio of surface area to the projected area on the horizontal plane. Thanks for watching and stay tuned for any further Green Valley tutorials.